Audiobook Academy Biography presents Archimedes. Archimedes, circa 287 BCE, Syracuse, Sicily, Italy, circa 212–11 BCE, Syracuse, the most famous mathematician and inventor in ancient Greece, was born in Syracuse and died in Syracuse. The relationship between the sphere's surface area and volume, as well as the cylinder that surrounds it, was discovered by Archimedes. Archimedes is most known for his hydrostatic principle, known as Archimedes' Principle, and the Archimedes screw, a mechanism for lifting water that is still in use today. At his early years, Archimedes may have been to Egypt, but for the majority of his life, he lived in Syracuse, the primary Greek city-state in Sicily, where he had close ties with II, the king. Letters from Archimedes to leading mathematicians of his time, including as Conon and Eratosthenes, were published. In 213 BCE, when the Romans laid siege to Syracuse, he played a vital role in the defense of the city by building war engines that were so effective that they prolonged the capture of the city. Archimedes was murdered at the sack of Syracuse by Marcus Claudius Marcellus, a Roman general, in the fall of 212 or spring of 211 BCE. As a result of his mechanical genius, Archimedes' biographical story is more widely known than that of any other ancient scientist, but it is entirely anecdotal. There are two spheres attributed to him, one a star globe and the other a mechanism, the details of which are uncertain, for mechanically simulating the motions of the sun, moon, and planets, which Marcellus is said to have brought back to Rome. While it's possible that his narrative about his jumping out of a bath and rushing naked across town shouting "Eureka! I've discovered it!" is real, it's also possible that it's just a popular embellishment that he came up with the concept in the bath. All of these stories are false, but they are all popular reflections of his real interest in catoptrics, the branch of optics dealing with the reflection of light from mirrors, plane or curved, mechanics, and pure mathematics. He was also said to have said, "Give me a place to stand and I will move the earth," and that a Roman soldier killed him because he refused to leave his mathematical drawings. Apparently, according to Plutarch, circa 46 to 119 CE, Archimedes was so disdainful of the practical inventions that he excelled at and owes his contemporary renown to, that he never wrote anything about them. However, despite the fact that all he is known to have written was theoretical, his fascination with mechanics had a profound impact on his mathematical thinking. Even though he wrote extensively about theoretical mechanics and hydrostatics, his treatise Method Concerning Mechanical Theorems reveals that he used mechanical reasoning to help him uncover new mathematical theories. Accomplishments. Archimedes left behind 9 Greek treatises that have survived. A sphere's surface area is 4 times that of its greatest circle, in modern notation, S equals 4r2, and the volume of a sphere is 2/3 that of the cylinder into which it is inscribed, leading immediately to the formula for volume, V equals 4/3r3. These two results are presented in On the Sphere and Cylinder, in 2 books. Upon making the second discovery, Archimedes was so ecstatic that he left instructions for its commemoration by way of an inscribed sphere on his tomb. A century and a half after Archimedes' death, Marcus Tullius Cicero, 106–43 BCE, discovered the grave, which had become overgrown with plants. Pi, the ratio of a circle's circumference to its diameter, can be found between the values of 3/1071 and 3 1/7 in measurement of the circle. When determining, Archimedes' method of inscribing and circling regular polygons with many sides was followed by everyone until the introduction of infinite series expansions in India and Europe in the 15th and 17th centuries. There are accurate approximations, in terms of integers, to square roots of 3 and numerous huge numbers in that work. A conic section, circle, ellipse, parabola, or hyperbola, revolves around its axis and creates segments of solids with varying volumes. Those are integration issues in today's parlance. See calculus. Many of the properties of tangents to Archimedes' spiral, which is defined as a point moving at constant speed in the direction of a straight line that is itself rotating at constant speed around a fixed point, are developed in on spirals beyond the straight line and the conic sections. Only a few curves were known in antiquity. There are 2 publications devoted to the subject matter of plane equilibrium, or, more precisely, plane centers of gravity. In both cases, it is referred to as equilibrium of planes. For the first volume, Archimedes claims to have established the law of the lever, which states that magnitudes balance at distances from the fulcrum inversely proportional to their weights. In spite of the fact that most of that book is definitely not real, consisting as it does of poor later editions or reworkings, it seems likely that the underlying idea and, possibly the concept of center of gravity were established on a mathematical basis by scholars before to Archimedes. What he added was a conic section extension of those principles, which is what set him apart. Using both mechanical, such as the way described below, and standard geometric methods, quadrature of the parabola shows that the area of each parabola segment is 4/3 the area of the triangle whose base and height are the same as that segment. Again, this is a fault with the integration process. In the Sandreckoner, a little book meant for the general public, but with a profoundly creative mathematics that is addressed to Gelen, son of Aaron. By showing how a big number, the amount of grains of sand that would fill the entire universe, can be expressed using the Greek numerical notation system, it aims to correct the system's shortcomings. In other words, Archimedes invents a system of notation based on a base value of 100 million. As far as we know, he had no prior knowledge of the Babylonian place value system with a base 60. Archimedes developed an inventive method to determine the sun's apparent diameter by observing it with an instrument in this work, and it provides the most complete description of Aristarchus of Samos' heliocentric system, circa 310 to 230 BCE. Method of Mechanical Theorems is an account of how mathematicians discover new ideas. As far as we know, it's the only work from antiquity or any period that addresses this issue. As Archimedes explains in this book, the mechanical approach he used to arrive at some of his most important findings, such as the area of a parabolic section, as well as surface area and volume, of a sphere, is described. Dividing two figures into infinite but equal strips and weighing each pair against each other on a notional balance yields the ratio of the two original values, which is then used to calculate the ratio. Despite its usefulness as a heuristic tool, Archimedes warns that this procedure is not a rigorous proof. On Floating Bodies, in 2 books, is only partially preserved in Greek, the rest is a medieval Latin translation from the Greek of the Greek text. Archimedes is widely acknowledged as the father of hydrostatics for his work on this topic. According to their shape and variance in specific gravity, distinct solids floating in a fluid will adopt different locations. The Archimedes Principle, which states that a solid denser than a fluid would be lighter by the weight of the fluid it displaces when submerged, is established in the first book. As far as mathematics is concerned, the second volume is a work of genius that has never been rivaled in antiquity or even since. Using geometric and hydrostatic variations, Archimedes establishes the several states of stability that a right paraboloid of revolution adopts when floating in a fluid with increased specific gravity. Other writings of Archimedes have been mentioned by later authors, but they have not survived. Catoptrics and the Cattle Problem, preserved in Greek epigram, are particularly interesting, as are his treatises on refraction and the 13 semi-regular, Archimedean, polyhedra, those bodies bounded by regular polygons, not necessarily all of the same type, that can be scribed into the sphere. Archimedes is credited with a number of works in Arabic translation that cannot have been written by him, despite the fact that they may have Archimedean aspects in them. The Stomachion, parts of which also remain in Greek, deals with a square divided into 14 pieces for games or puzzles, as well as a collection of lemmas, propositions presumed to be true that are used to prove a theorem. Both are concerned with rudimentary plane geometry. The mathematical proofs and presentations of Archimedes show considerable audacity and originality of thought, while also matching the greatest standards of modern rigor in geometry. While the method shows that he arrived at the formulas for a sphere's surface area and volume through mechanical reasoning involving infinitesimals, in his actual proofs of the results in sphere and cylinder, he only uses the rigorous methods of successive finite approximation that Eudoxus of Cnidus had invented in the 4th century BCE. In all of Archimedes' writings on higher geometry, establishing results concerning areas and volumes is done using these procedures, which Archimedes was a master of. Unlike the proofs of the earliest practitioners of integral calculus in the 17th century, when infinitesimals were introduced into mathematics, their mathematical rigor stood out. However, Archimedes' accomplishments are just as outstanding. In Sand Arithmetic, Reckoners the same disregard for traditional thinking can be seen, which demonstrates a thorough knowledge of the number system's essence. Hipparchus, the greatest ancient astronomer, relied on Archimedes' measurements of the solstices, which he made in the 3rd century BCE. Archimedes' astronomical interests and practical observational abilities are revealed in Sand Reckoner, but nothing else is known about this area of his work. Although a set of numbers has been passed down to us attributed to him, it has been revealed to be based on a Pythagorean hypothesis that associates the spatial intervals between the planets with musical intervals, rather than with observed astronomical facts. There is excellent reason to conclude that Archimedes is the author of such metaphysical theories, despite the fact that they are found in the work of an astronomer. Influence. As a result of the scale and originality of Archimedes' accomplishments in antiquity, the impact of his mathematics was very minor. Some of his conclusions, like the formulas for a sphere's surface area and volume, became mathematical commonplaces, and one of the limitations he set for 22/7 became the standard approximation throughout antiquity and the medieval period. Despite this, his mathematical work, as far as we know, was not developed in any significant way in ancient times, despite his desire expressed in method that its publishing would encourage others to uncover new ideas. When some of his works were translated into Arabic in the 8th or 9th century, some medieval Muslim mathematicians were inspired to match or improve on his accomplishments. However, he has also had an impact on other aspects, such as determining the center of gravity and geometric construction challenges. Since medieval Islamic mathematicians were influenced by their study of Archimedes, they produced numerous notable works. For later mathematicians, Archimedes' work had the greatest influence when manuscripts derived from Greek, and finally Greek itself, were printed in Basel, the Editio Princeps, in the 16th and 17th centuries. Foremost mathematicians and physicists of the time such as Johannes Kepler and Galileo Galilei were influenced by Federico Commendino's translation of Archimedes' works into Latin in 1558, which led to a greater understanding of them. Mathematicians of the 17th century, including René Descartes and Pierre de Fermat, were greatly influenced by David Rivault's 1615 edition and translation of the whole works, including the old commentaries. The growth of mathematics in Europe between 1550 and 1650 would be impossible without the rediscovered ancient mathematicians, among whom Archimedes was the most important. It is a pity that the method remained unknown to Arabic and Renaissance mathematicians. It was only found in the late 19th century, because Archimedes had hoped that the work would be valuable in the discovery of theorems through its publication. Thank you for listening in Audiobook Academy. Don't forget to subscribe and smash that like button for more content like this. See you in next video.